Alright, so last class we derived impulse momentum theorem. Looking at this formula, what needs to be true for momentum to be conserved? Well, this right side here is change in momentum, right? So momentum being conserved means change in momentum is zero. If change in momentum is zero, that means net force must be equal to zero. This is what's necessary for momentum to be conserved. Now, technically, this is the net external force acting on an object or a system. So even if one object exerts a force on another object, if the forces those two objects exert on each other are the only forces that are significant, we can say that momentum will be conserved for a system. For example, we've got a man standing on frictionless ice holding a ball. What's the momentum of the man-ball system? Well, he's just standing there. So that's zero. Net external force on the man-ball system. Well, there's gravity up, normal down, but those are going to cancel out. Net external force is zero, which means the system of the man and the ball together will conserve their momentum. So if the man throws the ball forward, what's the net external force on the man/ball system? Well, the man exerts a force on the ball, and Newton's third law, the ball exerts a force back on the man, but that force is part of the man-ball system. It's coming from within the system that consists of the man and the ball. So the net external force is still normal up, gravity down. So the net external force is still zero. If we take the point immediately after the throw. What's the total momentum of the man-ball system going to be now? Well, it's going to be zero. But the man and ball will each have momentum. So in this situation, momentum is conserved. So we can say initial momentum equals final momentum. Our initial momentum is just plain zero. Our final momentum, we've got the mass times velocity of the man plus the mass times velocity of the ball, and they will add up to zero. So you could, do stuff with this to figure out. If you're given three of those values, you can find the fourth one. So part F, the man is mass 75 kilograms, throws the ball 1.1 kilograms with a velocity of 8.5 meters per second west. Oh, I'm sorry, what am I doing? 75 is the mass of man, velocity of man, we don't know, plus mass of ball, times velocity of ball. It's west, I'm going to make west negative. So when we move that to the other side of our equation, it becomes positive. So we have 1.1 times 8.5, divided by 75. So the velocity of the man will then be about 0.12 meters per second. It came out positive when I plugged in a negative for west, so that means that it is eastward. So the total momentum of the system is still zero, but each of the man and the ball has momentum. The father and daughter are out ice skating. We talked about this same situation with Newton's third law. Father and daughter are out ice skating. Father's more massive than his daughter. They stand still, push off each other. So we got dad and his little daughter. They touch hands, push off. So who experiences a greater change in momentum? Well, what's our initial momentum? Is zero. And we can say that the net external force is zero. So the final momentum is zero. Therefore, dad and daughter have momenta, that's full of momentum, that add up to zero. So each has equal magnitude of momentum. Same magnitude of momentum. One in one direction, one in the other. Who experiences a greater change in velocity? Well, the daughter. Change in momentum is the same. And change in momentum equals mass times change in velocity. So smaller mass means greater change in velocity. Okay. Another situation, 2 astronauts playing catch outside of their space station. What's going to happen? I'm not going to write out a full answer to this, but you can listen and jot down whatever you want to remember. So, first astronaut, he's got the ball. Well, when he throws the ball, the momentum of the system of him and the ball is conserved. So the ball gains some momentum that way, which means he gains some momentum this way, starts drifting back. When this guy catches the ball, he takes some of that momentum from the ball, and he starts drifting back. Then he throws, giving the ball momentum that way, which means that he gains momentum this way, and he goes back faster. And then he catches it and goes back faster. Then he throws it and goes back faster. So they will move away from each other faster and faster. They'll get faster with each catch and throw. And eventually they won't be able to throw it fast enough to catch up to the other guy. But the total momentum of the system will remain 0, well, if we're neglecting any effects of gravity, which, of course, they would be pulled by gravitation, but we'll say they're in some imaginary place where gravity doesn't exist. Yeah, that's what's going on there. Here's another situation. A bomb is hung from the ceiling with a string, then it explodes. So after the explosion, what's the total momentum of all the pieces? Well, what's the momentum of the bomb before the explosion? It's 0. Net external force, also 0. The explosion is coming from inside the bomb, so it's an internal force. So the total momentum of all the pieces afterward is just 0. Net external force is 0, so momentum remains constant. Okay, do a couple of example problems. Excuse me. Spaceship with mass 1,100 kilograms is initially at rest, moves by burning rocket fuel, and in the process ejects gas. Change in momentum of the gas is what provides the impulse to move the ship forward. True statement. The spaceship fires its rocket, reaching a velocity of 5.2 meters per second while shooting 12 kilograms of that gas backward. What's the velocity of the expelled gas? Now, in reality, this is going to be more complicated. We're going to simplify this and say that all this gas is being shot back all at one time. In practice, it's more complicated because masses are changing as we go along. Yeah. So, what's going on? So we've got a spaceship, and the only thing exerting force on the spaceship is the gas. The only thing exerting force on the gas is the spaceship. So we can say initial momentum equals final momentum. I should have specified this in the problem statement. We'll say this is including fuel, including its rocket fuel. So it's the total mass of the spaceship plus the rocket. So initially, we've got a spaceship chilling out at rest. So initial momentum is 0. In the final, we've got the spaceship, but now the gas is no longer in the spaceship. So we've got a spaceship of mass 1,100 minus 12. And the spaceship reaches a speed of 5.2 meters per second. Our final is mass of the spaceship, velocity of the spaceship, plus mass of the gas times velocity of the gas. So we can calculate the velocity of the gas there. 1,100 minus 12 times 5.2. Move that to the other side. Divided by 12. And that will get us that the velocity of the gas is about 470 meters per second. I should have said magnitude or something, but in the opposite direction of the ship's motion. Two more examples. So, skateboarder with mass 68 kilograms is on his skateboard, which has mass 0.98 kilograms. They are moving at 2.3 meters per second east. The skateboarder jumps off, and the skateboard is then moving at 0.52 meters per second west. What is the skateboarder's horizontal velocity? Well, we can say initial momentum equals final momentum. Initially, the skateboarder and his skateboard are moving together at 2.3 meters per second east. Afterward, the skateboard is moving at 0.52 meters per second west, while the skateboarder is moving at some unknown velocity, so we can calculate what velocity he would be moving at. So that comes out to 2.3 meters per second, and since it's positive, that would be u squared. So another example, a wagon with mass 11 kilograms is rolling along the ground at 3.8 meters per second. A bag of rice is dropped into the back of the wagon, and the wagon's speed decreases to 2.9 meters per second. What's the mass of the bag of rice? Well, now in this case, I want to make note that in this case, the momentum in the vertical direction would not be conserved. You've got a bag of rice moving downward, and then it stops. So in the vertical direction, the net force is not zero. There's a normal force that's bigger than gravity to bring the rice to a stop. But in the horizontal direction, we can say that momentum is going to be conserved. In the horizontal direction, we've got a wagon moving along at 3.8 meters per second. And then, bag of rice is dropped. Well, dropped means it's going straight down, so it doesn't have any initial horizontal momentum. But then afterward, they move together. So we've got the wagon plus the bag of rice moving together at 2.9 meters per second. And we can do algebra to figure this out. 11 times 3.8 divided by 2.9 minus 11. So the mass of the bag of rice. It was 14 minus 11 sig fig, so mass of the rice would be about 3 kilograms.